So we're going to look at a constrained optimization problem, and I've done this in single variable calculus. Now we're going to do it with Lagrange multipliers so you can see both videos. A rectangular building is to cover 20,000 square feet, and then there's zoning regulations that say there must be 20 feet of space both in front and back of the building for entrances, loading docks, and other miscellaneous structures. They also require 10 feet of space on each side of the building. So we want to find the dimensions of the smallest piece of property which can fit the 20,000 square foot structure. So we have our building, which we know has to be 20,000 square feet, and then zoning, let's say, we don't know its area, so let's maybe call this y and this side x. So we know that x times y has to equal 20,000. So that's our constraint. Now we need our objective function, the one we're trying to minimize in this case. And so what we'll do is we need to add on those zoning restrictions. So let's say these are the sides. So those need to have an extra 10 feet that way and an extra 20 feet this way. And then we have this new larger rectangle, which is the one we're trying to minimize the dimensions of. So remember that these each had to be 20. So that makes this whole side x plus 40. Similar, these each had to be 10. That makes this whole side y plus 20. So we got the function we want to maximize. So we'll call it f of xy. And it's the area of those two, so x plus 40 times y plus 20. So let's move this so we have some room to do some work. We'll call our constraint g of xy. And so now we need our partials. Now first, if we want, we can go ahead and we can simplify this, or could just say, actually from here we can do it, f sub x equals, well, the derivative of this is 1 and 0, so times that is going to be just y plus 20. F sub y is going to be similar, derivative of that's 1 plus 0, so x plus 40. And so I am using the product rule here. I'm just kind of doing a shortcut version. Now we need the partials of g of xy. So g sub x. And now we only think of this as g of xy. We don't include the 20,000. That'll be our constraint equation. G sub x is just y. G sub y is equal to x. And now what we're going to do is set these partials equal to each other involving lambda, and we'll get our system. So we have y plus 20 equals lambda y, x plus 40 equals lambda x, and then the last part of our system comes from our constraint equation here, which is that x times y equals 20,000. Solving this system will give us our minimum. So what we want to do, there's many different ways to go about solving this system. One that I think works well in a problem like this is we may want to solve for lambda in both of our equations here. So solve this guy for lambda, solve it for y in terms of lambda, and we'll get y equals 20 over lambda minus 1. Similarly, for x, we'd get 20 over lambda minus 1. Sorry, not 20. 40 over lambda minus 1. Okay, so I'll leave that for you guys to check. That's what we get when we simplify those, and we'll plug those in for our x and y here, because that'll give us something all in terms of lambda. So 20 over lambda minus 1 times 40 over lambda minus 1, which is equal to 800 over lambda minus 1 squared is equal to 20,000. So we need to solve this guy for lambda. So what I'm going to do is I'm going to cross multiply the lambda. So right now I have 800 equals 20,000 times 1 minus lambda squared. So we'll divide both sides by 20,000. And this actually simplifies kind of nice. Comes to 1/25 equals, sorry, I wrote that backwards. That should be lambda minus 1. Equals lambda minus 1 squared. Square root both sides. And we get 1/5 equals lambda minus 1. Adding the 1 over gives us lambda equals 6/5. And we will talk about what that 6/5 means in a little bit. Okay, so let's use that lambda to figure out what x and y should be. So x and y are here. So y is going to be 20 over 6/5 minus 1, which is 1/5. Dividing by 1/5 is the same thing as multiplying by 5, so 100 for y. X equals 40 over 6/5 minus 1, same thing. This is going to be 200. So those are the x and y that we need to use. And now the dimensions are going to be, now remember we had to add 40 to x and 20 to y. So the dimensions of the minimum are going to be 240 feet by 120 feet. So those are going to be the dimensions of the smallest area that fit. Now, what we've done is we've minimized the area of f of x, y. So let's talk about the meaning of lambda, because this is always interesting. Now lambda talks about the change in our objective function with respect to a change in our constraint. So what that means is if we were to raise our constraint, if our building was to go up by 1 foot, so if we were going to allow our building to be 20,001 square feet, we would expect the area of this plot of land to go up by 6/5 of a foot. So the area of the land is going to go up approximately 6/5 of a foot for a 1 foot increase in our constraint. Now lambda, just like a derivative, is a good local approximation, but it doesn't hold for outside of that. So the further we get away from these dimensions, the less accurate this will be. But it does give us an estimate of how much we'd expect our area to go up by if we increase the area of that building by 1 foot.